Now we're on to the hardest part, but I think the most important part. We're seeing true applications of these ideas to actuarial science in particular. Let's talk about the warranty. So we're still talking about refrigerators. You got a warranty. It's a great warranty for the person who buys it. You get $1,000 whenever it dies. To use on a new refrigerator, or maybe even to go to Disney World or something. Okay. You should choose the refrigerator. You need a refrigerator. As a warranty company, you need to make those payments whenever they die. So you better save up some money right now for future payments. Use a savings account, a really good one, hopefully. Some really good savings account with a really high interest rate, so you can save up money to make those $1,000 warranty payments. Of course, you also want to make money on this, so there's a question of how you do that. Maybe it's based on the charge of the refrigerator to begin with. It's an expensive refrigerator. That's why the warranty is good. So what you're really interested in is the present value. Now I'm going to use just a plain P to represent present value. It's a capital P because it's going to be a random variable of a future $1,000 payment. But the thing that's unknown is not the amount of the payment, but its present value, because you don't know when you're going to make it. You also may not know the interest rate, but for simplicity, we'll assume we know the interest rate. How do you find present values? Say the refrigerator dies at time capital T. It's a $1,000 payment there. You got to go back to time 0. You got to multiply by an exponential decay, e to the negative interest rate times t, right? We talked about this last Friday. It's $1,000. The present value would be e to the negative 1,000 times e to the negative interest rate. Let's pretend it's 4% times t, the time that you make the payment. It's a new random variable created from an old random variable. I'd be interested in the exact same kind of questions. 1, what's its distribution? 2, what's its mean? 3, what's its median? 4, what's its standard variance and standard deviation? Its mean especially, I think, would be really useful because that tells you on average how much you should save right now to make everybody's payments, warranty payments in the future. You know, and different people, their refrigerators are going to die at different times, and you want to be able to cover everybody for a long time, forever, effectively. In reality, of course not, but theoretically, you think about that as forever. So what do? Let's focus on the mean. What's the mean of P? There's 2 ways to find it. An easy way and a hard way. Let's do the easy way first. But the hard way has got benefits. The main benefit of the hard way is it's going to give us the distribution of P, which will help us find the other things like the median and the variance and the standard deviation if we wanted to, but we won't take the time to today. The mean of P can be found as an integral of this function of capital T, though I'll use a lowercase t down here, times the PDF of T itself. That's analogous to what we did before, right? Integrate T times the PDF to find the mean of T. Integrate T minus mu squared times F of T to find the mean of T minus mu squared. Likewise, we can integrate this function times F of T, 1,000 e to the negative 0.04 t times F of T, use lowercase t's here, over the entire domain, in general minus infinity to infinity, but for our example, F of T is 0 when T is negative, so we can start at 0. This is for our example. Okay, this is the easy way to do it. though it doesn't mean you wouldn't make a mistake. F of t is lambda e to the negative lambda t. Let's have Mathematica do this. Change the function right here to being 1,000 times e to the negative 0.04 times t. I'm going to put negative 0.04 in there as negative 1/25 so that the formula comes out nice in Mathematica. That is negative 0.04. And there it is. Mathematica seems to be saying that this is 25,000 lambda over 1 plus 25 lambda is the mean of P. What does this equal? It depends on lambda. It's really a function of lambda. I could even graph it. If lambda is 1, is 25,000 divided by 26. This is if lambda is 1. $961.54. If on average your refrigerators are lasting 1 year, and you got to make $1,000 warranty repayment when they die, you should invest $961.54 for every refrigerator that you are insuring. You would probably want to play it safe and invest a little bit more, but at least invest this much. If, as another example, they last longer, like 10 years, so that lambda is 0.1, we should not have to invest as much. 25,000 times 0.1 is 2,500. 25 times 0.1 is 2.5. We'll get 2,500 divided by 3.5 is $714.29. If you know on average the refrigerators are going to last longer, like 10 years, you don't need as much money to invest now to grow to what you need to pay for all these people. This is an average. Okay, what's the hard way to do this? A lot to show you. The hard way is not just for the sake of doing something hard, but it's got benefits. It's going to show us the entire distribution of P. How do you figure out the distribution of P? You first try to figure out its CDF rather than its PDF. At least this is a simpler way to do it, I think. Capital F. Sub P, to emphasize it's for P. What should I call the variable name? How about lowercase p? But lowercase p's are hard to distinguish for uppercase p's, so I'm going to use a cursive p. Capital F sub capital P of lowercase cursive p. P is the present value random variable. It's a dollar amount. Lowercase p is a possible value it could have, which, by the way, it would have to be less than or equal to 1,000 because it's based on $1,000 payment. That is, you're finding the present value of. It's got to be less than or equal to 1,000. It's the probability, PR, that capital P is less than or equal to little p. What am I trying to do here? I'm trying to find a formula for this, an ordinary kind of formula. How? Relate this to T. Capital P equals this function of capital T. Use that. Replace capital P with 1,000 e to the negative 0.04 times capital T. Keep this as a lowercase p, though. If I'm going to use the known distribution of capital T, I better maybe solve this inequality for capital T. Seems like a reasonable thing to try at least. Let's see what happens if we do. First, divide both sides by 1,000. So you get probability that e to the negative 0.04 times capital T is less than or equal to lowercase p over 1,000. Now take the natural log of both sides to get rid of the e. Natural log, it is important that natural log is an increasing function so that the inequality here does not change direction. natural log function's increasing, so it preserves inequalities. However, in the next step, when I divide both sides by negative 0.04, that switches the inequality around. Switches the direction, like that. That's a P here. That's not so clear. A lowercase p right there. Which seems like that's a bad thing, because we've always dealt with less than or equal to's in these probability statements. And by the way, dividing by negative 0.04 is the same as multiplying by negative 25. Seems like that might be a bad thing. But with probabilities, you can work around it, because the probability of t being bigger than something is 1 minus the probability that t is less than that something. That's a law of probability. And the less than could be converted to a less than or equal to. It's not a big deal, because it's continuous variable. And this, oh, and I changed to P instead of PR. Change that to a PR. This is capital F for T evaluated at negative 25 ln of P over 1,000. What is capital F of T? That was 1 minus e to the negative lambda t. Use that. This now becomes 1 minus, in parentheses, 1 minus e to the negative lambda times negative 25 ln of P over 1,000. Yeah, that. Distribute the minus sign through, the ones cancel. You're left with e to the 25 lambda ln of P over 1,000. Kind of complicated looking, but that does simplify, because you can use properties of logarithms to write that like this. And then the e and the ln are inverse functions, so they cancel effectively. And you're left with the function P over 1,000 to the 25 lambda. P takes on values less than 1,000. Less than or equal to 1,000, and actually never 0. It's that kind of interval right there. This is the distribution of P. The CDF, actually. CDF of P. Its graph, it depends on lambda, but like, for example, if lambda is 1, that's going to be a graph that looks like this. And when you get up to 1,000, it's going to have a value of 1. That's what its graph's going to look like. To find the PDF from this, I just differentiate. This is a capital F, CDF. PDF is a little f, derivative of capital F. Hang with me, almost done. The PDF, little f sub P of P, is going to be the derivative of capital F sub P of P. Differentiate this with respect to P. It's just a power function. Bring down the 25 lambda. Subtract 1 from that exponent. With the chain rule, multiply by another factor of 1 over 1,000. It's going to simplify to 0.025 lambda P over 1,000 to the 25 lambda minus 1 for P between 0 and 1,000. Is it really right? The final punchline. Mathematica, save me. Did this work? For one thing, does it integrate to 1? Over the interval from not from 0 to infinity, but 0 to 1,000. 0.025 times lambda times P over 1,000 to the 25 lambda minus 1 power. Doesn't look like it's going to work, does it? It does. 1. What's the mean? I got to multiply it by P before I integrate to find the mean. Now let's change this back to a 25 over 1,000 here. What's the mean? 25,000 lambda over 1 plus 25 lambda. We saw that just 15 minutes ago. Amazing. It's working. But the bigger benefit is this is the distribution. And I could use this as a model then for values of P to go beyond just finding means, medians, and standard deviations, but a more comprehensive model. Again, I'm not saying it's accurate. It depends on the situation. But theoretically, it could be accurate if this is a good model.